On this video, we will talk about the application of volumes, and we're going to do that through some word problems. So let's get started. Let's take a look at example 1, and it says Shay has recently begun kickboxing and he has purchased a training equipment as a model in the diagram on the right. So here's the training equipment, and now the total weight of the base, the pole, and the on-field base is 270 pounds. So if we would have weighted the equipment, that would have been equivalent to 270 pounds. In addition, we know that the cylindrical base is 18 inches tall and also has a diameter of 20 inches. The dry sand used to fill the base, it weighs 95.46 pounds per cubic foot. And to the nearest pound, we want to determine and state the total weight of the training equipment if the base is filled to 85% of its capacity. So what we're trying to do here is we have an equipment and the total weight of the equipment it's of 270 pounds. And what we want to do to this equipment is the base, it's a cylinder, which can be filled with any substance, but right now we're going to fill it in with sand up to 85% of its full capacity. And the question is, since starting it was 270 pounds, what is the actual weight after the base has been filled in with sand up to or at 85% of its full capacity? That's the question that we want to answer. We start at 270. After we fill in it with sand, its weight is going to increase. What is the weight after the sand has been filled in? 85% of the base. So let's start by writing down what we know. We know that the initial weight of this equipment is of 270 pounds, which is what it was stated here. In addition to that, we also know that the sand that we're going to be using to fill in the base, its weight is 95.46 pounds per cubic foot. But notice that the base that we're trying to fill in, it's a cylinder. So let's find the volume of the base. But notice that the base, again, the base is a cylinder, so therefore the volume, it can be stated as 2 pi r times h. This is something that we discussed before. But notice that at least in this cylinder, we know that its diameter is 20 inches, so therefore its radius is just 10, and the height of the cylinder is 18. So let's just plug that in there. So now we know that the volume of the base is going to be pi times 10 squared times the height, where the height is 18. So therefore, if we simplify all this, we can say that the volume of the base is equivalent to 1,800 pi inches cubed. And notice that I'm just keep using pi because I want to work with the exact values. But an approximation, if you want to find the volume in approximation, you can get 1,800 and multiply by 3.14. But I'm going to keep it as pi. So what we know so far is that the actual total volume of the base, it's equivalent to this expression, 1,800 pi. But now the base is going to get filled in with sand. But notice one thing, the weight of the sand is given to us as 95.46 pounds per cubic foot. But we know that the volume, we only know the volume in units of inches cubed, not cubic foot. So notice that that's a conflict. It's a conflict of units. Sand is given to us as cubic foot, and we know that the volume is given to us in inches cubed. So we want to either convert the weight of the sand, either in inches cubed, or we want to convert the volume of the base as cubic foot. So whichever of those two, we just gotta make sure that the units match up. So that's exactly what we're going to be doing now. So let's convert some units. So I'm gonna call this conversion of units. And what I'm gonna do, I'm gonna get the volume of my base, which we already know that it's in inches cubed. And one thing is that I have it in inches. Let me convert it into feet so the units match up with the sand. Well, I know that in 1 feet or 1 foot, there's exactly 12 inches. But notice that what I want to do now here, I just don't want inches. I want to have inches cubed because I need to make sure that the unit on the top matches up with the unit on the bottom so they cancel out. So what I'm going to do here, since I know that this proportion is true, 1 foot it's equivalent to 12 inches. So therefore, 1 to the third feet cubed, it's equivalent to 12 to the third inches cubed. So if I know that 1 feet it's equivalent to 12 inches, so therefore, if I raise everything to the third, I will have the units that are going to match up here. And by doing this, notice that the units of inches cubed are going to cancel out with the units of inches cubed. So if I simplify this, what I'm going to have is the following. I'm going to have 1,800 pi, and again, the inches cancel out with these inches, times 1 to the third, which is exactly just 1, feet cubed over 12 cubed. And I notice that I have everything in feet cubed, which is exactly what I needed for me to use the units that are given to us for the sand. But if we simplify this, and again, you can double check with your graphing calculator. If you get 1,800 times 1 and you divide it by 12 to the third, this is going to be equivalent to just 25 over 24 pi. And again, the units just carry over. So what we have done here is we have said, look, I know that the volume of the base is equivalent to 1,800 pi inches cubed, but I know that it's going to get filled in with sand. So therefore, the units need to match up. So all I did, I converted the whole volume into feet cubed or cubic foot. And now that it's given to us in cubic foot, let's actually find the weight of the base. Let's actually find the weight of the base after the sand has been filled in. So now the weight of the base with sand on it is going to be equivalent to 25 over 24 pi times the actual weight of the sand, which is 95.46. And I think I'm just leaving the units out, which that's something that you definitely don't want to do. So let me just fix myself. So I know, and again, we need to write down the units. So I know that the volume of the base, it's equivalent to 25 over 24 pi cubic foot. So notice that if I multiply it by the actual weight, which is equivalent to 95.46, so the weight of the sand is 95.46. Take a look at the units. Pounds per cubic foot. So let's do that. So we're going to do pounds per cubic foot. And if we're going to be multiplying, notice that again, the cubic feet are going to cancel out. And now I got everything in terms of pounds. So now we know that the weight of the base with the sand is equivalent to 25 over 24 pi times 95.46 pounds. But be careful with this statement now, because this is the actual weight of the whole base. So what we have found out is what would have happened if we would have filled in the whole base with sand. It would have been equivalent to this much pounds. But we don't want that. We want to know what is 85% of it. So to find 85%. So, so now to find the weight of base with 85% of sand, we're going to get our statement 2524 pi times 95.46. We're going to multiply now by 0.85. Because now what this is saying is that if this is the total weight of it, if I multiply by 0.85, that will give me 85% of the base. So now we got this in pounds. And if we compute this, if you compute this on your calculator, this is going to be equivalent to approximately 266 pounds. So what we know so far is if we were to fill in sand on the base at a capacity of 85%, then the weight of the sand, so let me actually match it with the color, then the weight of the sand is going to be approximately 266 pounds. But what we wanted to answer is, to the nearest pound, can we determine the total weight of the training equipment? So we definitely have enough information to answer that question now. Because now the total weight is going to be equivalent to the initial weight plus the weight of the sand. So let's compute that. I know that the initial weight was equivalent to 270 pounds. And the weight of the sand, we found out that it was equivalent to 260 pounds. So if we add them together, this is equivalent to 536 pounds. So there it is. The actual weight of an equipment who has been filled in with sand on the base at 85% capacity, it's equivalent to 536 pounds. So now let's take a look at problem number 2. It states, a bakery, it sells hollow chocolate spheres. The larger diameter of each sphere is 4 centimeters. The thickness of the chocolate of each sphere is 0.5 centimeters. And determine the state to the nearest tenth of a cubic centimeter, the amount of chocolate in each hollow sphere. We also know that the bakery packages 8 of them into a box. If the density of the chocolate is 1.308 grams per centimeters cubed, can we determine and state to nearest gram the total mass of the chocolate in a box? So let's have a visual representation of this situation here. So we're talking about hollow chocolate sphere. So let's just draw that. So let's just draw our sphere of chocolate here. So let's assume that this is a perfect sphere, which is made out of chocolate. And what do we know about this sphere? Well, what we know about this sphere is that the largest diameter of each sphere is 4 centimeters. So if we were to measure the diameter of this sphere, that is equivalent to 4 centimeters. We also know that the thickness of the chocolate of each sphere is 0.5 centimeters. So if we got our chocolate sphere, we know that at least the thickness of it very bad sphere, but I hope you get the idea here. So the thickness of the chocolate that is in this sphere, let me just fill it in. So the thickness of this chocolate, it's of, um, I guess I'll do it here. The thickness of this chocolate here, it's a zero point 0.5 centimeters. So from here to here, that's zero point 0.5, and from here to here, that's zero point 0.5. And what we want to know is, can we determine to the nearest 10 of cubic centimeters the amount of chocolate in each hollow sphere? Now, we want to determine how much chocolate there is in this thickness of zero point 0.5 centimeters. So how can we compute that? Well, we can compute the amount of chocolate by computing the outer sphere minus the inner sphere. And what do I mean by outer sphere and inner sphere? Well, let's assume, um, let me see if I can do this. Let me see if I can, oh, that's the thinness. So this is what I'm going to be considering the outer sphere. It's just the sphere that will be at the surface of this chocolate ball. So it's just, this is the outer sphere. Now, the inner sphere is going to be where it ends, the thickness of this chocolate. So notice that here we have two spheres. We have the sphere that perhaps you would have seen outside of the chocolate, which is the outer sphere, and this is the inner sphere, which is where it ends the thickness. And notice that if I compute the outer sphere and I take away all this material, which is labeled as the inner sphere, what we're going to end up with is just the thickness of the chocolate, which is exactly what we want to find. So this is how I got this expression. The outer sphere minus the inner sphere, it will give you the thickness of the chocolate. So let's compute this. Now, since they're both spheres, we know that the volume of a sphere, this is equivalent to 4/3 pi r squared. So to compute the outer sphere, we need the radius of the outer sphere. Where at least I know that for the outer sphere, I know that its diameter, it's 4 centimeters. So definitely the radius is going to be equivalent to half of that, which is 2. Now, let's think about the inner sphere. For the inner sphere, I know that from this point to this point, that's 4 centimeters. But this thickness is a zero point 0.5, and this thickness is a zero point 0.5. So definitely the radius, the diameter of the inner sphere is going to be equivalent to just 3. Because think about it, from this point to this point, it's 4 centimeters. This thickness is 0.5. This thickness is 0.5. So 4 minus 0.5 minus 0.5. So we got a diameter of 3. So therefore, the radius of the inner sphere, it's equivalent to 1.5. So let's compute the volumes. So the volume of the outer sphere, that's going to be equivalent to 4/3 pi times the radius of the outer sphere, which we know it is equivalent to 2. So we got to 2 cubed. And I just noticed here that I wrote down square, which, well, it is cubed because we're looking at volume, minus the inner sphere, where the inner sphere is 1.5. The radius is 1.5, so definitely we have 4/3 pi 1.5 cubed. This on a graphing calculator, but let me just simplify a little bit more. Notice that we got two terms and they both have 4/3 pi in common, so let me just factor it out. So now we're going to have 2 cubed, which is exactly 8, minus 1.5 to the third, that's 3.375. And if we simplify right here inside the parentheses, so now this is equivalent to 4.625. And again, if we leave in the units out, they're all centimeter cubes. And if we compute this on a graphing calculator, it's going to be approximately 19.4 centimeters cubed. So what we know so far is that the volume that is present on the chocolate, it's equivalent to 19.4 centimeters cubed. But that's not the question that we wanted to answer. What we wanted to answer is, or what we ultimately wanted to answer is that if the bakery packages 8 of these chocolates in a box, and we know that the density of a chocolate it's approximately 1.308 grams per centimeter cube, we want to determine to the nearest gram the total mass of the chocolate in a box. So what we want to, in order for us to answer that question, what we want to do is we want to compute the density per chocolate. What we know so far is that the amount of chocolate in this sphere, this hollow sphere, it's 19.4. But we also know that the density of the chocolate it's approximately 1.308 grams per centimeters cube. But now notice that we don't have the same problem as the previous example because now the units of the volume matches out the units for the density. So we don't have to do any of that unit conversion rate. So all we can do is just multiply it. So we're going to multiply 19.4 times 1.308. And what we're going to end up with is 25.34 grams. So we know that for every ball of chocolate, this hollow ball of chocolate, a hollow sphere of chocolate, there's exactly, or approximately, shouldn't say exactly, but approximately 25.34 grams of chocolate. Well, if the bakery packages 8 of them in a box, and if we want to answer the question, the total mass of chocolate in a box, we know that for every chocolate, 25.34 grams of chocolates are present, and there are 8 of them in a box. So to properly answer the question, the total mass of the chocolate in the box, all we gotta do is just multiply them. So each ball has 25.34 grams, and each box has 8 of them. So therefore, the total box is just a multiplication of those two, which is approximately 2.272 grams. But notice that the question states to the nearest gram, so we're just going to round this to 203. So let's just recap what we did in this problem. Well, first we wanted to find out the amount of chocolate. And the way that we did that is by looking at two spheres, the outer and the inner. To find the amount of chocolate, we did the outer minus the inner. That will give us the chocolate that is present in this hollow ball. Then we say, well, this is how much chocolate there is present, 19.4 centimeters cubed. We know that for in the chocolate, their density of the chocolate is 1.308 grams per centimeter. So to find the density, we multiply the volume times the density rate. That's how we got the actual weight or the grams of chocolate in the balls. And after that, we know that there were 8 of them in a box, so we just multiply our result by 8, and that's how we can get the total mass of the chocolates in the box. And with this, it concludes our lesson for application of volumes.